Alright guys, welcome back to a new video. In this video, I'm going to be talking to you guys and explain to you guys what Big O is. I'm going to do this through 5 different parts. First, I'm going to talk about what Big O is, and I'm going to introduce you to the different notations that we use in Big O. Next, I'm going to talk a little bit more about these notations and what they mean. Third, I'm going to show you examples of code for some of these different notations. Fourth, I'm going to show you a graph of these notations. And finally, I'm going to show you an example in Python and implementation of binary search, where we're also going to be implementing a big O to the log n. Alright, so that's the game plan for today. Without further ado, let's jump right into the video. Okay, so before I actually get into the video and I start talking about the notations in Big O, I first need to give you a pretty good understanding of what Big O actually is. So if you search up Big O notation in Google, you pretty much get 2 main definitions. So we have Big O notation is a mathematical notation that describes the limiting behavior of a function when the argument tends towards a particular value or infinity. We also get Big O notation is a way to measure an algorithm's efficiency. It measures the time it takes to run your function as the input grows. Okay, so as we take both of these definitions, we can say that Big O is a way of measuring the speed of your algorithm as your data grows. Okay, or Big O is a way of measuring the efficiency of your algorithm as your data grows. Okay, so I think we have a pretty good understanding now of what Big O is. Let's go into the depth and now talk about the different notations in Big O. Okay, so I'm going to be now covering these notations and later giving you guys examples of these notations. Okay, so first we have Big O to the 1. So this means that your code is constant no matter how much data you feed to it. So, for example, dictionaries in Python, no matter how many keys and values you have, when you try to search up a key, it will always have a constant time, or roughly the same time, as whether you have a million keys in the dictionary or whether you have 3 keys in the dictionary. Okay, so this is because they use something called hashing that I won't cover today. The second one is Big O to the n. So this means that your code speed is linear. So, so as your data grows, your code slows down. Okay. The third one is Big O to the n squared. And this is quadratic. Okay. I'm not going to be talking too much about that today. The fourth one is Big O to the log n. And this we use with binary search, which I will be talking to you guys in the end and showing you guys the implementation in Python. Big O to the n cubed is also another notation that I won't be talking about today. And our last one is Big O to the n factorial, which I will also not be talking about today. But there are some more notations, but we're going to be covering these 3 mainly today. Okay, so before we go to the next step and I show you guys the graph of these notations, I'm going to be showing you guys an example on the whiteboard for number 2, because I am going to be covering an implementation and example for number 4, and I kind of already talked about an example for number 1. Okay, so if we want to have the Big O of n, maybe this is something that, some practical code that we could write that we would have a Big O of n. Okay, so pretend that we have this list, and it's from 0 to 100. Now what we want to do is we want to get 100. We want to loop through this list and find what index 100 is at. Or, yeah, 100 is at, okay? But pretend this is not a sorted list. So actually, instead of 100, let's say 57. Okay, so this is not a sorted list, so keep that in mind. And so we have to find this. So an example of how our code could be a 0 to the n is if we made this for loop that said for I in range and then basically what we want to do is we want to loop through this whole list and we want to check if whatever, and we want to just check if that element that we are on is 57. And then maybe we can just break. Okay? So this code is 0 to the n because if we have 100,000 elements in this list, and by the way, big O, we can think of it as the worst example for this, okay? So let's think of it as the worst possible scenario. And if we have 100,000 keys, 100,000 elements in this list, then it will the time to look through the whole list would gradually increase for the amount of elements in this list. So you can see the more data, aka the elements in this list, the more data, as the data grows, the elements in this list grows, the time that it takes for us to look through this whole list grows. So that is an example of big O to the n. Alright, great. So now let me show you guys a graph of all these different notations and some more. Alright, so I pulled up this graph of big O from the interwebs and I want to talk to you guys a little bit about this. Okay, so in this graph, the x-axis is our input size and the y-axis is our time. Okay, so we have 4 different lines on this graph. We have big O1, we have big O(n), we have big O log n, and we have big O n squared. Okay, so let's talk a little bit about these. So let me say this blue color for big O1. So big O1 is just constant. So you can see on this graph, it is just constant right over here, and it'll always stay constant. And yeah, so it's pretty clear on this graph. And also, it's the time. The time is a lot less than all the other lines on this graph. If we look at the highest point, big O1 is the lowest out of these points. So you can clearly see that big O1 in the long term is the best way to go. Next, we have big O log n, which is on this graph the second best big O, and you can see we kind of have this curve over here. When the input size is low, but then as you can see, when it gets bigger and bigger, it kind of settles down. And even though it's still increasing, it is not as big as when the input size is low. Okay, and going into now let's talk about a big O n. So you can see this is fairly simple. It's linear, and it will just grow as the input size increases. So it's just linear. And then we have big O n squared, and you can see this kind of has a small curve here, and then it just shoots up exponentially as our input size gets bigger. And that kind of makes sense. As our as n gets bigger, the numbers that it's squared by also gets bigger. So you can see it just continues to grow, but also the input as the input size slightly gets bigger and bigger, you can see the time is still shooting up. So it's that's pretty cool. But one more thing I want to talk about is in the lines where the input size is very less. So let's just look at this kind of section right here. And let's talk a little bit about this. Okay, so we can actually see for most part of this small this small input size, we can see that actually the constant big O1 is actually the highest point. So actually, instead of making our input size when it's small that big, let's actually shrink it down to over here. And this point kind of right here. And here we can kind of see that for the most part, sorry, one second. For the most part, the constant big O1 is actually the highest point. So everything else kind of starts around here, but the constant starts over here. That's because it does take some time to actually create this constant, right? And that time when the input size is very less, is actually what is it actually takes longer than the actual algorithms to run. So you can see that not always is big O1 going to be the best big O. It will be in the long run, like big O1 and big O log n are going to be the best way to go in the long run when your data is very big. But in the short input size, it's a lot different. So that's kind of all I wanted to say for our graph. I will put this PNG in the description down below if you'd like to check that out. But let's go on to implementing big O log n in Python. Alright guys, so here is the implementation in Python for our log n and for our n. Okay, so first I'm going to be explaining to you guys about what binary search is, because the implementation for nlog is just a binary search. And then I'm going to be running both of these, and I'm going to be showing you how our code is much faster using log n than n. So it's the same purpose of this code, but we can see if we structure our code as nlog, that it's much faster than log n. All right, so first let me explain to you guys what binary search is. So basically what binary search does is it first finds the midpoint of our list, and keep in mind that it has to be a sorted list, and it checks if the number that we're trying to find is greater or less than the midpoint. If it's greater, then it cuts the list in half, and if it's greater, then it should cut everything or delete everything in the list that's less than the midpoint. And if it's less than, it should delete everything that's greater than the midpoint. Okay, so then every single time that we run through this binary search, we are cutting our data in half. Okay, so eventually we'll come to a point where we only have one element, and that will be our element. So let's go through this code, and I'll show you guys this implementation and how it follows what I just said. So first, we just have our list, which is 1,000,000,001 elements long. Then we have this while loop that loops through this binary search until we have one element in the list. Finally, and then finally, when we have that one element, then we have found our element, and we should break away from this while loop. And you can see that's here. But before that, we have our two if statements that just check if the midpoint is less than 1 billion or if the midpoint is greater than 1 billion. So if it's less than 1 billion, you can see it creates a new list with the midpoint being the least number and the greatest number being -1. So you can see that we just cut off this half, and then if the midpoint is greater than 1 billion, then we do the opposite. So then 0 would be the first element would be our least, and the midpoint would be the greatest, because now we know that a billion is in the middle of these two. Okay, and as I said earlier, finally, when we have one element, it will break this loop because it's not either greater or less, so it'd be equal to. Okay, so finally, when it breaks it, we're just going to get our end time, and we're going to print done with the amount of seconds that it's taken. All right, so keep in mind before I run this program that it may take some time earlier because we are appending a lot of elements to this list. So if you're wondering why it's taking so long, yet it's printing out like zero point 0.0 seconds or zero point 0.1, it's just because it has to run through this code first before it even gets to this code. Okay, so and then this end function, this is just looping through the whole list and just checking if it's 1 billion. So it should run through 1 billion iterations. All right, so that is binary search for you, and that is the implementation in Python for O of n. So now let's run this code and see what happens. So first let's print n log. All right, so let's run this and see how long it takes for n log. So it should take a few seconds here. As I said, it is looping through 1 billion and 1 elements. And while we're doing that, let's talk about how this, as I kind of said in the graph, how when we have less data in our list, it actually doesn't really make a difference, whichever one we choose. And actually, n would be faster. So maybe later, what we could do in another video, I could show you guys the n of log, and I'll show you guys n. So actually, after this, I'm going to show you guys n log and n, and I'm going to show you guys it when the range of the list is very low, so maybe like 1,000. And we'll see that it doesn't really make a difference whether we choose n log or n, as I kind of said when talking about the graph. Okay, so you can see it's just completed, and it said that it took 0 0.0 seconds, and that's fairly fast, but you can see we still have to append to this list first. All right, so now let's run n. And this should take a pretty long time. When I ran it earlier, it took about 37 seconds for n. So we'll see how that does. But till then, let's fix our code to look at data where or the example where the data is very less. So let's just take this range down to 1,000 and just make this, or we'll say 1,001, and make this 1,000. Also make this 1,000, and then we can just make this 1,000 too. And that's it pretty much for fixing our code. If you guys would like, I'll put the code of this implementation in the description so you guys can kind of play around with it and check it out. You can see it's still not done completing. Maybe for the next one we can also show the iterations because it's not very much. So let's also change that. So Let's also here just print out our new list, okay, just to show how the list is increasing. You can see it still hasn't finished. It's taking a very long time. So finally, after about 76 seconds, it's finished finding 1 billion in the list. So that's a really great example of how this takes a very, very long time as our data grows. So let's quickly just run this code that we coded while we were waiting. So you can see for n, it finishes really quickly, and for n log, it also finishes about the same amount. So actually, it doesn't really, I guess, amount in seconds when our n and n log are running in the low data. So you can see how it really increases as our data grows, though. Maybe just for the fun of it, let's add 2 zeros to these two. Okay, let's run n log. All right, done. And now let's run n. It's also done. You can say it takes a little bit longer, but it is done. All right, so that's about it for our example of n log and binary search. And I guess that wraps it up for our 5 parts in this video. Okay, so that wraps it up for today's video. Thank you guys for watching this video. I really appreciate it. If you guys have any questions about this video, feel free to put them down in the comments. Or if you have any comments on this tutorial, please also put that in the comments down below. If you like this video, please hit the like button. And if you'd like to see more videos like this, please subscribe to the channel. Once again, thank you guys for watching this video. Really, really appreciate it. And until next time, peace.